Right, Sarah, I believe you have a question?
Yes. It was on question 51 and 80.
Sorry, which questions?
51 and 80.
51 and 80.
Yes. For the first one, how did the equation?
Sorry, let me see if I can actually get to it. 51, okay. You were saying?
What is the derivation of the equation? Like
The derivation? Is that what you said?
Yeah.
The one that they give you?
Yeah, like where did the AE to the negative AR over R minus?
Oh, talking in the solution. A is just a constant given in the problem.
Mm-hmm.
Are you? What is the question? Just how to do it, or?
Basically, yeah. Like where did that equation come from?
All right. The relationship between the electric field and the electric potential is that the electric field is the gradient of the potential. Is if the potential only depends upon the radial direction, we can simplify it into negative dV dr. And they give us V, and we know that A is a positive number. So we're just basically taking the derivative of V naught e to the, forgotten already. 51 negative AR over R. Negative AR over R. So we're just basically taking a derivative. I keep going. That dramatic pause there was for any questions. V sub naught is a constant, so that can just come right out. So I've got negative V sub naught, and now I'm taking the derivative of this part right here. I have two functions of R in a sense. First off, I'm going to rewrite it as R to the negative 1 e to the negative AR. Just because I never remember the quotient rule. I always have to put it in terms of multiplication. Come on. I have to put it in terms of multiplication, and now I just use the not chain rule, product rule. So I have negative V naught, derivative of the first one, negative R to the negative 2, e to the negative AR, plus R to the negative 1, derivative of the second one, which is negative A e to the negative AR. Dramatic pause for more questions.
Okay, I think it's just that I forgot the rules of derivative.
So if I have a function, y is equal to xz, y prime is equal to x prime z plus z prime x.
Okay, yeah, that makes sense.
Okay. And you're good from here, or do you want me to finish it up?
I think I'm good.
Okay.
Yeah.
Anyone else?
I had a different question on a different question. Or a different.
I think I know what you mean. All right, and you also have a question on 80,
Yeah.
and then you have a question still. Is your question
It's
on
also
80?
on 80.
All right,
Okay.
two birds, one stone. So we got a figure, we've got the wire, the uniform charge per unit length. What is the electric potential at point P? Well, symmetry means we only have to really do, we don't have to do the whole problem, we can just figure it out, double up some of it. Let's do it over here. So I got a line, semicircle, line segment. Assume uniform charge distribution. And uniform charge per unit length. So we have lambda, 2.25 times 10 to the negative ninth coulombs per meter. Let's see, this is 0.75 meters. 0.75 meters, and the semicircle, 0.25 meters. All right, so we're finding the electric potential here. So in essence, I have three segments here. I've got left segment, right segment, and the semicircle. I know the left segment and the right segment will give me the same answer, because the electric potential is a scalar. Whatever sign I get from this, I'll get the same sign from this one. I don't have to worry about any directions there. And then I've got the semicircle, which is relatively simple mathematics, especially compared to what we're about to do. So if I have a line segment here, at some point that's 0.25 meters, and that's 0.75 meters. I know the formula of electric potential for a point charge. For a point charge, the electric potential, KQ over R. But we have a line here, so I have to create a point charge. So I take a little segment right here, I'll call it DQ. It's infinitesimally small, thereby making it a point charge. This distance right here would be R. And so dV is equal to K dQ over R. Now, I need to get it in terms of a single, I can integrate both sides, but I have two variables here, Q and R. K is a constant. I'll pull that out. So I need to get this in terms of a single variable, so I need to relate dQ to R somehow. And I know that the lambda is dq dx. And I need to somehow resolve x and r. So why don't I define x to be from there? So x plus r is equal to 1. And this is an r, not a v. That prime there is just a straight mark. So this is equal to k times the integral of lambda dx over r. I know r is 1 minus x. So I have this is equal to k integral lambda dx over 1 minus x. So lambda is a constant amount. I now have, in terms of a single thing, limits of integration. So that's going to be k lambda integral dx over 1 minus x from 0 to 0.75, because I defined x to be from here, and so the smallest value of x is 0, the largest is the length of that line segment. K lambda negative natural log of 1 minus x from 0 to 0.75. Oh, actually, plug and chug, we end up with K lambda, excuse me, times the natural log of 1/0.25. So 9 times 10 to the 9th, 2.25 times 10 to the negative 9th, times the natural log of 4. Calculator exercise at this point. That's the hardest part of the problem right there. So questions on this part?
In the solution on here, you had bottom as negative x. And I was trying to understand where the negative came from.
All right, let's see what they did. That was problem 80. So they defined they set their basis here. That's 0. X is, well, it depends on which way they went. Take that. Good. Thank you. Sorry, I always hated it when teachers looked at my test before I walked out, so I apologize.
I don't care.
They're defining to the right as positive, so think of a number line here, so x, if that's 0, that's negative 0.25, and that's negative 0.75. R would be, so R and x are synonymous, except for the fact that R is a distance, x is a position. So if I'm all the way here, R is equal to 1, x is equal to negative 1. That is my interpretation of what they did.
Okay. I mean, I noticed if you didn't have the negative, it would be a natural log of a negative number, would obviously not work.
Generally frowned upon. So they ended up with it plus, oh, then they did the semicircle. And then the other part, okay. Yeah, that seems overly righty. Anyway, that's the belief. If I had just chosen, if I had kept it at positive x, find x from here, going that way, the same as r, then it would have been 0.25 to 1.
What?
And that just double it.
Oh, in the solution it says ln of negative x. Is it?
Yeah, well, let's see, the relationship here, they defined x differently than I did. They defined x to be from here. Well, they defined x to be, there's 0 and x is positive to the right. I defined x from the left-hand side of the problem. So, in this, the way they did it, r equals negative x. If I'm over on the left-hand side. Follow-up questions? You seem unsettled, Sarah.
Oh. So we did 1 minus x because.
Did 1 minus x, because I defined x to be from the left-hand side here. R is from the point in question. In this formula right here, R is how far I am from where I'm trying to find my potential. So I define R, well, R is defined from our point here. X I define from over here.
Okay.
And so x would be positive the entire time, the way I defined it. And so x plus r is equal to 1. And so So R is just 1 minus X. All right, Patrick, was your question answered?
Yes.
All right, Sarah, was that the same issue you had about the negative X, or do you want me to finish it up?
Oh, it was about the semicircle, like where did the
Okay.
pi r come from?
All right, for the semicircle, so I have a semicircle here, and I need to find the potential at this point. Again, I can take a small little segment, create a point charge so that, and then I have that distance R there. So I can use the point charge formula, so that's equal to K. Try that one again. So the potential from that infinitesimally small part is K dq over R. dV, so if I integrate both sides, I get V from 0 to V, or good enough. K is a constant, and for the semicircle, R is a constant. So I can bring R out. And I'm left with just the integral of dq. The integral of just the differential and nothing else is just q. If I think about starting here and I'm working my way around, at this point I have no charge, but a charge accumulates as I go across. So this is just K over R times Q. Now, I don't know the charge specifically, but I know the linear density. I know that lambda is equal to Q over length. And so my charge for the semicircle is going to be lambda times the length. And the length is it's a semicircle, so it's pi, or lambda times pi r.
Pi r is the circumference, right?
Pi r is, does count as the circumference of a semicircle? 2 pi r would be a full circle, that's half of that. So we end up with K lambda pi.
Okay.
Questions?
The r is outside because it's a constant, right?
Right, for this situation, R is a constant.
Okay.
There are other ways of approaching the problem, but to me, this was the simplest of them.
Okay.
Other questions? Ben, you look just ready to go.
Yeah, at this point, I'm just focusing.
All right. Do you have some questions? I don't remember what quiz questions are, so just in case. Here we go. Yep. Just had them in my hand. It's the flash. There we go. Begin when ready. All right, questions? All right. I want to start out with one of the homework problems from chapter 27. You have a capacitor configuration. Each capacitor is the same, has a capacitance of C. It is infinitely long, and the question is, what is the equivalent capacitance? So let's start out with the end one here. That's C, C, and C. What's the equivalent capacitance?